Hello, I'm Doug Sweetser. This talk is entitled Quaternion Quantum Field Theory, One Method to Calculate It All. It was supposed to be presented at the fall APS AAPT meeting at Brown University, but it turned out there was no room in the inn, or at least on the schedule, and so I'll probably do it in spring 2011. But since I prepared the talk anyway, I'll go ahead and record it and put it up here on YouTube. So I wanted to give you a bit of the backstory. I've been having a lot of really productive chats about my unified standard model work with a physics graduate student in Charlotte, North Carolina, Lowell, and he's actually the lead salesman for the Unified Field Theory t-shirts in all of North America. But we usually actually talk about more technical sorts of things. And he said that he read this book, Quantum Field Theory Demystified, a self-teaching guide by David McMahon, and he thought it would be good if I read it too. And so I took him up on the challenge, and it took me about a week to get through the whole thing. And he said now the reason he recommended it was because he thought that I would think about issues differently. Now, I take this as a compliment. I mean, I hope it's a compliment, right? Thing is, though, I mean, I know how to embrace the standard approach, but I also know how to come at it at a different angle. And when I went back to reread it, coming at it from this different angle, it took me literally a month to get through 3 pages because I had to re-synthesize everything that was there. And this book is very direct, as it were. Lots of equations, a lot of nice, succinct descriptions of what's going on. Not a lot of proofs. So it was the kind of way I like to work. And in those 3 pages, he'd done the correspondence principle, the Schrödinger equation, the Klein-Gordon equation, the Dirac equation. So it may not have been long, but there was a lot of content. And this talk really is about those 3 pages and new perspectives I have on quantum field theory that came out of Lowell's suggestion that I get this book and think about it. So, let's get into a little bit of history. That new methods basically rewrite everything done in the past. Take, for example, special relativity. Lots of equations that are only about time or only about space. Well, those have to be reformulated into equations of space-time that use 4 vectors. And when you square that, you get that Lorentz invariant interval. And lots of equations about energy, lots of equations about momentum. But now with special relativity, you have to think about 4 momentum. And when you square 4 momentum, you get a Lorentz invariant mass. Now in quantum mechanics, there is the correspondence principle that says, hey, if you got a classical equation, I bet we can formulate a nice quantum mechanic one. And they have these complex amplitudes all over the place that you have to square in order to get real observables. But although you could rewrite every equation so that it works with special relativity, what physicists do in practice is they say, well, you know, if and only if things are really going fast, am I going to bother with special relativity? And for quantum mechanics, they say, well, if and only if those things are really small, and am I going to bother with quantum mechanics? Otherwise, that just won't bother. Well, what I want to do is write equations so that those extremes are always taken into account. I don't have to go, I wonder if stuff is moving fast or if this is small. I just want it to work, okay? To have one accounting system that will be true, you know. So what I have done is come up with one method with 4 rules to rewrite all equations in field theory. So the rules are, number 1, to keep the 4 vectors together using quaternions. Now, I know a good number of you are going to say, but I don't even know what a quaternion is. Okay, if you've had enough exposure to math to learn about scalars and vectors, a little history. Those were born in the same house. In fact, the house was called the House of Quaternions. But the folks who work with quaternions overpromised. They didn't deliver, and so you don't learn the history at all. But you know, in special relativity, it's not just that 4 numbers go together. It's that you have a scalar and a vector going together. Okay, there are more complicated structures than that too, but you can actually usually back down into a combination of 4 vectors, but it's usually going to be a scalar and a 3 vector that have to hang out together. And I don't think that's an accident, because that's exactly the same kind of structure as what a quaternion has. And you say, well, then why haven't physicists done this before? It's because if you can't deliver things like the Schrodinger equation, the Klein-Gordon equation, the Lorentz group, all these technical kinds of equations, if you can't do that, there's no reason to bother with them. And that's essentially the core of my research, is bringing these really central equations into a quaternion form. All right, rule number 2. There are no factors of I. Well, actually, there are. They're just implicit into a quaternion. You know how I said it's a scalar and a vector? That vector is not only a vector, it's a 3 vector. And it's got an I, it's got a J, it's got a K, guaranteed. Okay? So you don't have to, waste any pencil lead on it. Rule number 3 is to write out all constants. The folks who are professional, they use natural units because they are so good. They don't want to be bothered by these details. But Spinoza said the beauty's in the details, so I'm going to keep them. I know Feynman was someone who thought you should always write your units out, and he didn't like it in his day when natural units were kind of catching on. And believe me, they've really won over at least the theory people. But I'm kind of going retro. I'm going with Feynman on that one. And the 4th idea is to make all equations dimensionless. Now, I used to actually write that if possible. And I was like, well, who gets to decide if it's possible? If you're going to come up with rules, make them strict and then follow them, like, all the time. Because that way there's no question. It's like, I got these strict rules, I follow the strict rules, because nature seems to be like that. You don't catch nature sometimes like breaking conservation of energy. She just doesn't. And it's like, how can you be that consistent, man? I know I personally am not. So but nature is. So anyway, I like the idea of these rules because like none of them are like at all radical. I don't think. I mean, keeping four vectors together. Well, that's the message of special relativity. No factors of I. Well, I guess some people trained in quantum mechanics might get upset until they said, well, actually, they're always there. And writing out constants. Now, I know a lot of people are going to say, I'm not going to bother. It's like, good. Then you won't join my research team. But but at least for now, I'm going to do that. And I'm going to make things dimensionless. So let's just apply all this stuff by writing Newton's second law with the method, seeing that it actually uses zeros all over the place. So we have the standard way of writing it out, and that's just F equals ma. And then if we use this Quaternion quantum field theory way, you would go, oh, please don't show that to the children. They'll be scared. Okay? Because you got, wow, you've got H bars, you have G's, you have C to the 5 in there. It's like, but also notice that we have two scalar operators, that basically the time derivatives, and what those are multiplying. There's one time derivative. One time derivative there that has the Planck time. It's like classical physics. You're using Planck time. How absurd! That makes no sense. It's like no. This is dimensional analysis. This isn't about Planck. It's about making your time derivative operator dimensionless. That's all it means. Okay? And then you've got mass divided by a Planck mass. And again, I'm not talking about anything other than making this expression dimensionless. So that's got no units. And then, yes, we do have a dt of a dr, but that's a velocity, so we divide it by c, and that's also dimensionless. So the resulting expression, it has the ma term in there. It also has the rocket science term, which, of course, is sheltered usually from people starting out in physics, but rocket science is that second term there. And it's this factor of g over c to the fourth that makes this force dimensionless. And you'll notice actually that the h bar, kind of the calling card of quantum mechanics, is not there. And that's just the way it is. So let's just do an application here and think about gravity on the Earth. And you do this calculation and you go, oh, we involve g, small number, h bar, small number, and we divide by c to the 7th, which is a big number. It's like, whoa, you're really trying to make the acceleration I feel on this planet look ridiculously small. It's 4.42 times 10 to the 51 minus 51. Okay, I actually went around for a week going, I'm not comfortable with this idea. I'm so used to hearing 9.8 meters per second squared. Well, actually, earlier in my education, I think I learned it was 32 feet per second squared. And now you're telling me, or I'm telling myself, actually, it's got no units. It's like, that's okay. All right? And it's like, but how does that fit in with everything else that I know? That's what I was struggling with. I mean, if I can't use my meter stick, Well, I can use your meter. You can use your meter stick to make the measurement. You can use a watch with second hands to make the measurement. But you just report it in a way that it just has no units. And it's like a really small number. Now, think about this in terms of the message we're getting from cosmologists about the role that the planet Earth plays within the entire span of the universe. And you go, God, that is such a small role. It's ridiculous how incredibly insignificant. And actually, words fail here to say how stupidly small the Earth is. Okay? And so actually, this looks much more consistent with that cosmological message. I mean, a good 25-30% of the global economy is based on moving stuff around in our gravitational field here. But in terms of the cosmos, our gravitational field is like just really, really weeny. And this number is really, really weeny. And so it's consistent with that message. And the other thing I really like about it is that all those zeros are kind of the signal that we're dealing with something that's totally classical. If somebody says, is this equation totally classical? I mean, I don't know how to tell unless I kind of see it, broken into its generators. And if I see the generators, every one of them's got a zero in it, I'm go, you're doing some classical physics there. Now, it's a perfectly fine thing to do. I mean, I'm not disparaging classical physics in any way. It's just that it's nice to have a system to be able to spot it at work. All right, so now we're going to switch over to quantum mechanics. And we're going to try to write Schrödinger's equation using a full 4 derivative and a 3 derivative, specifically a spatial derivative. So here's the standard way of writing the Schrödinger equation that you'll find in Wikipedia and good sources of information. And you'll say, oh, well, the spatial derivative is on one side and the time derivative is on the other. Well, that is not consistent with the rules as I have laid them out. So I'm going to have to bring that over. Going to put them together. And there's that factor of I, so we can just cross that one out. But you see that's a second spatial derivative, but only a first derivative of time. And that's been known since Schrödinger's time, that there's that first order versus second order thing going on. Now, if you go and you make the quaternion operators to pull this thing off, the dimensionless ones, okay, so that h bar with a time derivative has units of energy. And so that g square root of g over h bar c5 is actually 1 over Planck energy. And so that thing has units of nothing. No units. Okay? And that's a full 4 derivative because we've got that del operator there. But then the next term, well, it's got unity, okay, as a scalar. We're not taking no time derivative, okay, so it's just a 1. And then we've got this del thing, and to make the del thing dimensionless, okay, we have to come up with, well, there are different ways to do it, but this is one way. Throw in an h bar over MC, and if you do that, you'll realize, oh, the m's cancel, oh, the times cancel, oh, I only have a length. And since the del is going to give me a 1 over length, that's going to be dimensionless. Very good. And then you go, hold it, and then you just kind of repeat it again. Well, I'm repeating it again, not quite. I throw in an extra conjugate operator. What's that going to do? Well, that's going to wipe out a 3 vector. And as you can see in this second line there, there is a 3 vector there that's got that's just a 0 sort of thing, and you see this scalar operator that looks like it's going to be able to do the job of the Schrodinger equation, because you've got a single time derivative with a single h bar. You've got an h bar squared going on. Now, the one thing I know people are going to say, well, oh, but do you have your factors of I all taken care of in the correct kind of way? Because the del, the spatial derivative doesn't have an I factor. The time does. Maybe you're messing up in that way. And I think the only real solid answer to that question is, let's just wait. I am through page 3 of the book, okay? And it is my full intention to go through the, 180, 190 pages of the book and do everything. I like to make really rigid rules. It's like, if I can't do something, then the hypothesis is wrong. Okay, I can't pull off this transition to Quaternion quantum field theory. So if you don't want to bet on my work, that's fine. But I have always, on this project, it's just kind of like, wow, that's a really, really hard thing to do. And if I give it enough time and imagination, it seems to turn out. And I think it just speaks of more elegance and more potential information than standard physics, because that 0 doesn't look good to me, to my eye. Perhaps you could say, well, it has to do with the Schrodinger being kind of classical quantum mechanics. I'm a little suspicious. I think that we might be able to get more information about quantum systems if we just didn't pretend like it wasn't there. And this is actually a recurring theme, that phases are often just ignored. So many people have written the Schrodinger equation like that, and there's just nothing wrong with also having a phase factor in there. But it ain't there. Oh, and believe me, huge volumes of work are done with Schrodinger's equation as is. And when I look at it, I see those zeros and I get a little concerned. All right, but that is classical field theory, which applies to a particle. And so now we're going to make the switch over up, as it were, to the Klein-Gordon equation, which actually keeps everything, even the phase. So this is the way it's written in the standard form. You've got second time derivative, you've got your del operator, you've got this this mass sort of thing squared. Everybody's squared, everybody acts on phi. And people say, isn't that beautiful? And I say, well, actually it's not beautiful enough, because you should keep your time and space derivatives together. I'm sorry if I'm sounding like a broken record. I'm a consistent broken record. Okay. What turns out to be really cool to me anyway is that you're basically calculating E squared minus P squared, which as we know is a relativistic, which is the Lorentz invariant mass. We're doing this using operators, but then we're kind of dividing through by the mass. That's what the mc squared is. And we've got unity over there. And unity is so important in quantum field theory because you think of the groups like U1 and SU2 and SU3, and they're always saying, I'm one, I'm one, I'm one, in different ways, but that comes up time and again. And, of course, somebody being observant, I hope you're observant, out there, they go, uh-oh, you got the sign of mass wrong. Therefore, you're wrong. You're an idiot. You're a complete fool. Because we've dealt with this signs of mass before, and it's supposed to be a minus sign on the other side, so that when you bring it over to this side, it'll be a plus sign, and you have 0. Again, I'm going to use the same. I don't call it a defense. I mean, I'm going to just say I got to see if I can solve actual problems with this as it is written. This seems the most natural to me. When I now look at the Klein-Gordon equation and I see it just doesn't make sense to my eye. You put scalars with 3 vectors. Okay, that's what dt and del's about, but you can't just tack on something else as is done. That goes on the other side of the darn equation, this equation just, the phase of this just looks gorgeous. 2 beta gamma squared, there's something cool about that. There's something cool about this time space derivative having to do with the phase, It's not completely about changing in space. It's not completely about changing in time. It's the two working together to tell you something about the phase of the wave function. I want to know what that can tell me about systems. And it could be that my education is not broad enough, but I don't know that many people discuss that sort of thing. And the reason I feel compelled to discuss it is because it comes up so naturally with this sort of formulation. All right. So that is my introduction to the method, and I'm just going to give you a bonus issue, and that is thinking about space-time graphs, because you remember how rigid I said the rules were. It's like you don't get a choice about making things dimensionless. Well, think about an event in space-time. Okay? And it's got a time, and it's got a space, a location. And if you divide the time by the Planck time, and you divide the space by the Planck length, then you will have a dimensionless space-time number. Now, again, these numbers will be really small. But if you're just thinking about an event being a finger snap, it had better be really small, okay? Because finger snaps are not important. Supernova, a whole galaxy, supercluster colliding with something else. Those matter. Those should have some significant numbers. But the stuff that we can do in the lab, they better be vanishingly small. And, well, now they are. Ordinary, everyday activity on the Planck scale. No, just made dimensionless by using these tools. I mean, the core reason I do that, I think, is because what you do with mathematics is you often say, well, why don't I just take the exponential of this, that, or the other thing, and why don't I take the cosine of this? Well, you can actually only do that if what you're dealing with is dimensionless, okay? Because what happens with exponentials is, you look at the Taylor series and it's 1, and then it's got this thing squared, and it's got this one, to the 4th power, it's got this one to the 8th power, I think there are odd ones too, whatever. But you're used to seeing that in math, okay? But if you've got something that's got some units to it, you can't do anything. You can't say, and I added the this x to this one squared. No, except the units no longer work. If everything you do is dimensionless, then you can do all this funky math to it, all this kind of standard math. And I do encourage you to take a look at this graph because it's kind of fun. It's got sines, cosines, and tangents, as we all know, those being the ratio of two sides. But what's far less known, or at least I'd never really heard anybody discuss it, is that hyperbolic sines, hyperbolic cosines, those were always like, I don't want to learn that. That's too hard. Well, doing this graph, I go, no, it's easier. It's just like the sine. It's just the opposite side of the triangle. Where the triangle is actually not built on a circle anymore. It's built on a hyperbole, okay, which is pretty similar to a circle, except it's got a minus sign. But otherwise, it's the same. And the cosine is going to just be the close side. The tangent is just going to be the hypotenuse. It's like, wow, that's kind of concise. That's kind of nice. I kind of like it. All right, so and I usually end up with a little slide about myself and say goodbye. I would just like to point out, though, that this is a big research project in terms of how much stuff has to be done in the future in order to validate it. I really have to do calculations with my Schrödinger equation to prove that, the factor of I thing doesn't make it just complete gibberish, all right? I have to show that my Klein-Gordon equation, even though it's got the wrong sign, actually, when you go do the nuts and bolts calculation, ends up with completely sensible, consistent with our standard approach sort of stuff. And that's a lot of work. And so I've set up this website, visualphysics.org. It shows up in bold there, with a preprint server, so that as I figure out stuff, I'm going to post it there, because I can't post the official preprint server. I am not an official physicist, and so they don't let me go there. And it doesn't bother me. We don't have enough substance yet at this point to say we've got a really valid alternative. But it's going pretty well. I have moved beyond the first 3 pages. But I keep going back to them, actually, and just making sure that it's as refined as can be. It's been a lot of fun, and I hope you've enjoyed this little introduction to Quaternion quantum field theory. Thank you very much.